wir hatten gerade schon das spannende Thema mit Power oder
Hello. Hello. This is talk about power, about computational power. At home, you work at City at Home for Search for Aliens. Dieter Kanzmüller will from the SuperMUC NG will give a talk, and the translators are Kaste and Tatzelbrum. We're translating the German to English. Hello. Hello. Thanks for the good introduction and good evening. You have noticed that he has said something wrong. This is not the talk in German. This is a talk in Austrian, but I'll put in an effort. The subject of the talk, SuperMUC NG, is NG stands for Next Generation, as in Star Trek. The subtitle has gotten lost, but that was important. Where are we in the race for the fastest computer in the world, and what does NG have to do with it? Before I want to start with the core motivation. It's about this. The Munich Tatort. There's a TV show was turned here. This is the people are not in the room here, but this was an interesting story because everything was toppled upside down because there was a movie turned and nothing worked. And in the background you see the SuperMUC. And that was a story. I don't want to tell you the contents of the story. It was about artificial intelligence. The interesting thing about this story was what happened to as soon as this was transmitted. On the next day, there were the first phone calls. The first calls were some newspaper that said, "What the hell are you doing here in Garching?" And then were questions like, "How dangerous is this? What are you doing? What else can you do with this apparatus?" And those are things where I thought about. And that's many people in the room have are in the same situation. Hardly anybody understands what we're doing, and this is the same thing with the SuperMUC. You might be the experts of the future of digitalization. You're closer to it, but it's about time that you're looking closer at what is such a supercomputer, what is a SuperMUC. One or the other who didn't see the Tatort might have seen a movie by Edward Snowden, and in this movie the SuperMUC is in there too because they were not allowed to take a movie at the NSA, and they asked us to do the movie at our place. And there are some scenes in there where SuperMUC is playing in the background. There are scenes also where our sysadmins, the people who administer the system, are running through the picture as cameos. That gives the movie more authenticity. And one of the pictures in the Snowden movie was this one, where I have to say that for copyright reasons I have done that myself. That's not in the movie, but you see the same thing in the movie, but the lights on top are off and it looks more futuristic. So what you see is SuperMUC phase 1 and phase 2. And there the deers are behind. SuperMUC 1 is what you see in the background, and the 2 rows in the front are the SuperMUC 2, and the room has 1,200 square meters, and it's pretty filled. The empty space is for the movie, for the TV show Tatort, the empty. The interesting thing is the power. The phase 1. 600 square meters is 3.2 petaflops, and the 2 rows in front are 3.6 petaflops. And everybody is supposed to know what a petaflop is. This is also he also wears the petaflop t-shirt. It's 10 to the 15th floating point operations per second. It's 1 with 15 zeros. And that was 1 petaflop is in calculation power, computational power. That's phase 1, 3.2. with 15 zeros and 3 point. It's actually 14 zeros because it's a decimal point. But okay, that's what they can calculate. And if the media call, what does that mean? It's 17. If it says 17,000 people at the 55, it's some billions of calculation power. This calculation power, what the devices are capable of. The interesting thing is that in 2012, the half of the room in the background had 3.2 petaflops, and in 2015, the 2 rows in front 3.6 petaflops. So within 3 years, we only need a quarter of the room and a third of the current and get the same computational power. And that's the increase in computational power. And that's the reason why we always get new devices, because there is a point where it's cheaper to get the new device than to operate the old device. And we see in this example that the computational power is based on the computational cores. It's 230,000 computational cores. The intention is that these computational cores calculate collectively in parallel, and that they use everything available, and they can use large calculations, and there's a memory requirements that match it, and there's a current requirements. In this case, it's the power consumption is a small city with 30,000 households. The free room in space is for the Tatort movie or Tatort show, and then we put this in there, and this is the SuperMUC NG, which is at the time Germany's fastest computer, which is 26.7 petaflops and 311,000 calculation cores, and they should all work together and be used for the application. Main memory is 307 terabytes. We have all the digital pages in the Bavarian National Bibliothek library, but they would comfortably fit in there. Before we go into the details, we go to the background. Why do we need such a system at all? Why did we decide to get that? There's the Gauss Center for Supercomputing. That's a society that's been created for the national computing things. The HLRS in Stettin, the Jülich Supercomputer Center, and the in Munich Center for the scientific community get the highest calculational power.
There have been agreements between the state and the federal state of Germany, so half and half between Bavaria and the national level. If you look at it closely, this is the proposal for the project for the time range of 2070 to 2025. In total, it's a sum of 450 million euros. We take care to construct those highest performance computing in order to support this kind of research that is done on for very high computing demand. We also have to take care that we select the projects that will have the ability to run on that system. So it's available to all of the German researchers, and they can propose projects that will run on this. There's a board with scientific members that select the projects that will be allowed to run. So there are specific requirements for the systems. If you look at the LSZ, which is the organization that runs the system, it should have a fairly broad spectrum of applications that can run on this. And there are the specific areas that we can that we look at it are the astro, geo, life sciences, and environmental sciences, as well as various areas of physics, fluid mechanics, and chemistry. So we take a closer look at this, and what I want to do is shed some light on certain aspects. In the past, there were students who basically did it as a job, that they were plugging together all the hardware and then install some software on it and then run the software on it. But here there's a bit more of a process around this and more requirements. 2016 we started a proposal in a platform called SimApp, where, if you think about it, 2016, the system was already installed, and we're now two years past this timeline. And if we now look back, that 2015 we installed the older system. That the result is that we basically, the moment we have installed it, we already have to think about constructing and designing the new system. So we went into a dialogue with the various partners to fix the legal requirements around this. We also have to put down the criteria and the guidelines in advance before constructing the system to show that what we're going to offer. There are also NDAs involved, and it also needs to match what we have regarding the space requirements and the cooling systems. So on the 23rd of January, the first applicants were bringing proof that they're supported in their financial needs and their economic capabilities. So in order to know if they also have to name a reference installation for us to prove for us that they can handle the requirements in regards to energy efficiency and cooling. So the question is, who is actually capable of constructing such a system? And there's only a very small number of companies around the world who are actually capable of doing this kind of thing. In the first round, we looked at 5 companies who are capable of that. We basically met with all of the applicants 3 times. They had to give us a proposal. This is a very interesting process that we went through. It took a lot of human capital that was involved in selecting the final contender. There were at least 25 people involved at any given time. So in the second round, after we went through all of the 3 rounds of the first 5 companies, we narrowed it down to 2. So both of them had the chance to basically give us the best offer. And we got this description of goods and services. I chose 3 that I wanted to show you. They have different colors. Red is mandatory. Yellow is what is important. It would be nice to have. Green is more of a... Those are target areas that we wanted to have, but not that important. So basically, this is like a whole list of questions that each vendor has to answer. It's basically, we want a complete description for every, as an answer for every question. For example, here, this is relating to cooling. So basically, we get a complete folder full of answers every time we put out one of these catalogs. And there's a few legal requirements around this, especially about antitrust and market protection. We're also looking at total cost of ownership, obviously. We said about 64 million. Sounds like a lot of money, but it's total cost of ownership. So the hardware, the system, the software, and the maintenance have to all be included, and it may not go over the limit that we set. So it's not possible that after the fact they come around and say, okay, we need a little more. This really is a strict requirement. The vendor that is making a proposal really have to make a good suggestion that whatever's left after the buying really needs to be enough for running the support for this. Otherwise, the companies themselves have to fund it out of their own pocket. This is a little different than what you do when you buy a laptop, obviously. We need the maximum power for the budget that we can get. So there's only going to be one vendor, and there's no side offers. And they're forced to work together. So there's a pretty big window for installing it. We said Q3 18 to Q4 19. So they still have some time to get their act together and to maybe form a partnership even. So it's often it's best for them to be in there earliest. There's a whole competition going on there between the vendors. And we're going to do measurements to prove the capabilities of the system and to measure the performance. And it needs to be tested in regards to functional capabilities. And there's also questions around the proposal where the vendor can ask us if they don't understand the questions that we're asking them. So we basically need to always replicate that question from the vendor to all the other vendors so they're in the loop. And this is a lot of effort for us. So we really hope that it's easiest and most understandable, so there's less effort for us. So in the end, hopefully everybody's happy, and we signed the contract, and you can see it I'm holding it in my hand in the picture. That's the contract that I had to sign. And hopefully every detail is in there. This was the 14th of December 2017. So in total sum, it lasted a year for us it took us a year to get this done. So here you can see the green InfiniBand cables connecting it. So those are the numbers that we got, and we're pretty happy about them. Those are the technical specs that we got for the final system. So now we're obviously interested in how we compare to all the other fastest systems in the world now. So let's look at them. There's a list that's called the top 500 supercomputers in the world. And those are the first 10 spots in the list. So there's obviously 490 more down the list. This is updated twice a year, once in June and once in November. Interestingly enough, there were 13,000, as a conference of 13,000 participants. It's interestingly enough, it's smaller than the 35C3 now. So this is the first system in the list. This is the fastest supercomputer in the world. It's called Summit, and it has an IBM Power 9 architecture and NVIDIA Volta GPUs. In total, it has 2.4 million cores, and it has a theoretical maximum peak. This is about 200,000 teraflops. This is only if the computer did nothing but calculate all the time. This is, of course, unrealistic. So this is really theoretical. If all of the cores really were doing nothing but computing all the time. So the second value is a lower value. It's the Rmax. It's called. This is an empirically evaluated measurement. It's the maximum performance gathered in the LINPACK. So I just want to mention Oak Ridge National Laboratory is one of the American supercomputing centers. They have codes, and we know all the codes. So the DOE and stuff. Interesting is also the power consumption. It takes about 10 megawatts in power. In Tennessee, the electricity is about a sixth of what it would cost here. So for them, it's not that important. For us, this is a lot, just because of the running costs.
Now we look at the first 5 computers. There's a competition, there's a race, and in the current list on place 1, and place 1 is US, and third and fourth is China, and then there's a Swiss computer. Those are prestige projects. And the presidents, like the current American one, are inclined to join in this competition. So the Department of Energy has these supercomputers, and they have no problems to get money. If they do environmental science, it wouldn't be as easy to get money. Naturally, they already have a nice competition. The computation, the computer on the third rank has a Sunway processor, which is an interesting processor. Now you see the connection to Politik and the NetPolitik. If you listen to the NetPolitics talk, there is a Chinese variation of that. The Chinese would have liked to build the Taihu Lite with Intel processors, but the American president said no, we have an export stop, and then China just built their own processor. And back then, nobody believed that would be possible, but they pulled it off in 4 years. And with the computational power that matches, and you see how important competition is. And if you look at the importance at the 5th place, that is a conspiracy theory that the colleagues in the Switzerland had added 2 more racks with additional graphics boards to get to 21.23 petaflops, because before they had 19.3. And if we look on the next list that I wanted to show, there was the SuperMUC is there, which has 19.5. This is a malicious assumption, but they wanted to be ahead of the SuperMUC. This picture here shows from the supercomputing the award ceremony. There's a framework here, like the occasion. You see the green annotations are the changes in the. And it says that in the top 10, our system is the third Chinese one, because it's been provided by Lenovo company. But in truth, we have a contract with Intel, and in that contract it says it's Lenovo that's listed and not Intel, and that's the contractual details. I can live with this being a Chinese computer. Now, if we look closer at our system that's on rank, 8th rank, we see that there is Lenovo, 305,860 cores, and for the LinPack we haven't used all the cores. We only used 305,000 cores. We have a theoretical peak performance of 26.8 petaflop. And 19.5 petaflops we reached in real life, and we don't have current measurements yet. We haven't done that yet. There are some improvements to be made. This is not the last thing that we did. Now we need to do some additional changes. Now, we talked a lot about LinPack. What is LinPack? LinPack is a solver for a linear system of equations from Dek-Jongara. We see a linear system of equations on top. This is a benchmark with 64-bit floating point operations in the paper that's described in detail. How does that fit to such a computer? If we scale this, if we have many processors, we need to look at the Amdahl's law, that the speed increase is increased by the sequential part, and Gustafson's law that we need to parallelize the problem to the amount of we need to scale the amount of data with the size of the computer. We are in the situation that it doesn't make sense to put in a computer with more processors if we don't have more data too. We can download this list as an Excel table, and we see the size of the problem, and the Nmax is the number of variables that need to be solved. And if we look further, and this is the do-it-yourself round, you can look at this on your own smartphone. There are the links. There's a Google LinPack app, and you can install that. And this is on an iPhone 6, for example, of my girlfriend. In this case, she has 7 gigaflops as computational power. with the same algorithm, and we have the possibility to compare what the SuperMUC is doing with what we have in our pants pocket, and we can compare the computational power. The interesting thing at it is that the comparability. We can also look in the past. We can also compare this to the fastest computer in 1988. We have 2.6 gigaflops. An iPhone 7 is 3 times faster than the fastest computer in 1988. One or the other might be older than born in 1988. You see how fascinating this development is. We also see the increase in computational power, the curves that shows how the computers become faster, how many floating point operations per second. We see an exponential growth. This is a log scale. In the 25 years since the beginning of the RISC, we had an increase of a factor of 2 million from than before. That ties into the previous talk. We are always getting faster. There's the Moore's law. This is Moore's law. I'm going to skip this. We also have this exponential growth in Moore's law. In the parallel computers, there's also a top 500 list. It's interesting to see that one of the reasons why they get faster is that the number of cores is growing. If we look at the list of 1993, there's between 10 and 100 processors. If we look at that list in 2018, there's everything. All the computers have about 100,000 cores, and the biggest ones more accordingly. And we can look at the accelerators, and there's a list here. And many of the supercomputers work with GPUs, with graphics processing. But many of them use accelerators, and they are distributed accordingly. The favorite one is the Tesla P100 from NVIDIA. The interesting thing there is that the SuperMUC doesn't have accelerators. Those are just pure Xeon processors. It's Intel Xeon Platinum 8174 processors. They have some properties that you can go up with the maximal clock frequency because we have water cooling. We have cooling effects. There are other properties. Those are which are top of the line. There's nothing else but computers in the processors in the laptop computer. It has the advantage that you can just upscale the codes from your laptops. You could theoretically run Windows on the SuperMUC, but that doesn't match the performance anymore. But the interesting thing is if we look at the water cooling. Here we see one of the boards. We see that the boards are double boards, where there are the 2 boards with 2 processors, and we see that these red and blue pipes are the water pipes. And if we look at it from the back sides, we see the water connectors in and out. And if we look at the whole rack, that it's how it's piped, how it's routed. We don't put in normal water. Usually you cool with 8 to 12 centigrade water, but the SuperMUC is cooled with water at the temperature between 40 and 50 centigrade. Why do we want to cool at 40 or 50 centigrade? Water still has very nice cooling properties, and the processor is still hotter than the 50 degrees centigrade. As long as the temperature difference is great enough, there is a cooling effect. The question is if the water has 60 or 70 degrees on the other side, how much energy do we need to cool it down back from 60 to 40 degrees? If we think about how it's like outside, we need zero energy to take the 40-degree water outside, 60-degree water outside. We need no cooling effort because we just cool it down by ambient temperature. And this is one of the cooling managers. And this is 3,000. We need 3,000 liters per hour per rack. But it's also clear that what we have there, the cooling manager, is twice as high as the racks. just in order to get all the infrastructure in there. And the double ceiling has a height of 1.80 meter, so that can all be put together. So that we do a few more tricks too. We don't need fans per node. We save a lot of electricity by that. We can scale down the jobs. We do job frequency scaling. We adjust the clock frequency so that it's optimal for the code that we run. There are some heuristics that tell us that, and we need 15%. We get 15% gain by cooling ambient water. That's we see the Leibniz Center with 5 buildings. There is this cube which has 10,000 square meters on 5 floors. You see on the floor, you see on the ceiling the boxes which are cooling 2 megawatts. And what's important here is that this is a cross section of the building, from the basement where the transformers are up to the super performance computer, that this all has to play together. Whatever we do needs to be a holistic approach, which is why we developed something where we optimize not just for the current consumption, not just the system software, but also the application that determines what current is required, and the building is designed to respond to the power requirement. And this is how the demand is. What happens with the demand is needed. You see the current consumption for one run of LINPACK, which is started around 20 o'clock, which is running into 9 a.m. And we start with 800, with only the 800 kilowatts when the operating system is just running. When the job is started, it goes from 800 kilowatts to 3 megawatts. And what's in addition is also cooling. So we need more than 3.5 megawatts. And that's what the infrastructure has to deliver, has to sustain. And once the job is started, that runs up and goes down again. And that sense, LINPACK is the peak load. And we can see that this curve for the current consumption, we see it's zoomed out. We have it's an odd amount of current, and there's a lot of optimization potential that we can do. On the other hand, is LINPACK also a reliability test for the infrastructure? We see a output box with the fuses. You also see the 2 power connections to the left and the right. Left the closed one, right the open ones. And what happened is that one of these LINPACK runs, the box looked like this. You see that the top of the lid has actually molten down by the heat that was produced in that box. Why does something like that happen? This also happens at home. Sometimes if you tinker with the wrong stuff, here it happens because here it's a problem is because the human that put that in didn't tighten the screws. So you had arcing, voltage arcing, and that heated up the box, and that has caused the failure. The LINPACK is the benchmark to find out what problems happen. And this is kind of a secret that we use LINPACK for failure checks. These are the transformers. This is the transformer number 11. There are at least 11. There are actually 12 transformers. And this was at the open house. That was interesting because I went there out at 8:30. I thought that everybody was out. Most of the people were over there, and there was a massive loss of power that was caused by the transformer number 11. That's if you see the sign, it has 1600 kilovolt amperes that it can provide. And if we look at the log files, then we loaded the transformer with 1500 kilovolt amperes. And why did it fail at 1400? And we learned something. We learned that by the dust that was on there, even though we kept the maintenance intervals, the dirt made the transformer so hot that it switched off. And then the other transformers tried to compensate, and they couldn't compensate it, and then the whole house threw off the power. And that was at 8 hours open house. And that has occupied the queue until 2 a.m. There's also a diesel that is for the uninterruptible power supply. That's also interesting. If we look at the whole system, if we look at this LINPACK, who cares about LINPACK? Who cares if this is position 8? It's nice to say that we're in the rank, and LINPACK tells us where the technology state of the art is, and we understand better how the system performs under peak performance. If we want to, we can also use a different benchmark, and at the SSSP benchmark we're rank 1. At BFS benchmark we're 5th rank. But that's not it.
What we really want is to provide a system that the scientists can work with. This is nice to have, this result in the LINPACK, but what we really want is that the scientists are able to do things that they couldn't do before. So this is one of the examples. This is about phylogenetic trees. This is from Alexis Stamatakakis, sorry, from Heidelberg. It's about insects and their genome. His interest is, how are these insects related? Can we relate can we find the relation between the different types of insects? And then we're going to try and figure out the relationship between them. So he does sequencing and then alignment, and then he's trying to do trees. They're called phylogenetic trees. So because this is a lot of different data points in the genome, you need a supercomputer for this. So this is the number of possible trees for 150 species. It has 301 different digits. Just if you want to look at 150 different species. And he was, the scientist was waiting on the SuperMUC to arrive because he knew he had the code. There was no computer that could run this. So he had to wait for SuperMUC in order to solve this type of scientific problem that he had. And it's not so much about the performance in itself. It's more about the memory that it provides it, because the data that he's crunching is so huge. And he needed to bring all of this together in order to solve this scientific problem. So, well, what's in it for us? Well, not really. We just have to supply him with the capability and support him. But this is, he was able to publish a paper in Science, and this is the actual thing that we're after. So we did our job because we helped him get into it, and he did it on our computer. Well, no, he said if it works for the bugs, maybe it works for the birds. So he got another one out of it. This is not much about money or power. This is about getting capabilities that we didn't have before. So they just issued a new post stamp about simulation about species and about the phylogenetics of species and about astrophysics. We provide them with things where they can do new methods. So this is another nice example. We got a lot of good prizes for this. So, for example, the highest performance computing prize, we were in the finals. There were two different groups that worked together: the geophysics group from the LMU and the Institute for Informatics from the TU. What they did was they simulated a volcano. They looked at the shock waves from an earthquake within the volcano, and this is the kind of order of magnitude that we're talking about here. Those are 1.4 petaflops from 150,000 cores roundabout. This is about 44.5% of our peak performance. So in their normal run, they almost got 45% of our peak performance, which is, so this is the point where we're asking, why are we doing this in Germany at all? We could basically go anywhere and work with them. For example, in Oak Ridge, we could go there and just have them calculate our things, but what we can't have is get the whole machine, because they obviously have their own jobs that they want to run. So the differentiator for us is that we can actually provide the whole machine to someone. That's why we're doing it here locally. So if he really, really has something important, he can have the whole machine to himself. You can't do that anywhere else in this order of magnitude. This is why we get more progress this way. If I had another hour, I could just show you more examples, but I don't. The nice thing about it is the examples are all really different. Those are also more applications where you can see the whole spectrum of things that we can do here. So computational fluid dynamics or astrophysics or solid state physics, geophysics, material science, and so on. It's really interesting if you look at the distribution of the computational time according to different disciplines. You can really see the fluid mechanics needs the first third, physics needs the next third, and then the material sciences are next. Informatics is really small if you compare it. Those are things like AI or other things that are starting to grow in those kind of in informatics, but in the computer science. But it's really interesting for me to see all the different applications that these other disciplines are utilizing us for. So if you analyze what you get out of this and you see how many different systems are being employed, and what you can see here, we've been computing for 7.6 billion hours. There were 5.6 million jobs that were being processed, and 2,000 researchers as a client. And the breadth of the applications that we see is unique worldwide if you really look at it. What you see here, this is our report on the whole system that you can take the barcode if you want to look at it. It shows all the different applications that you get out of this system. It's really interesting. You can download it if you want, if you're interested in that kind of thing. There's also a science symposium that we recently did where we showed the applications of the future. There's really interesting new projects coming up. You can look it up on the website. So if you go back to the list, the top 500 supercomputers, the race for the fastest system, we're actually getting something that's very usable in regards to development of new technology and computing power. But in the end, this is something like Formula One. The fastest computer is about as relevant as who won the latest race. This is not something that all of science is gonna profit from. So we have to put this into relation into the kind of effect. It might be nice to go for a run with a Formula One car, but I have a friend who's living in Ho Chi Minh City, and he sent me this picture yesterday. This is the Kong Ho Street. If I visit him, then we always do our trips with the moped. When you're a tourist, there's no chance. You just have to walk around, and you can do things like this. Basically, this is a normal way to go to the office over there. This is cheaper and faster than if they were taking a car together. It's just a relation. You just have to put it into relation of what you really want to do. So this gets me to my last remarks. What I wanted to talk about, but I didn't have the time for. I knew this in advance, obviously. What's the next step? We're all in front of the barrier with the 10 to the 15. What's the next step? So the next thing is the exascale, the exaflop barrier. Then after that, there's the zetaflop. Who will reach it first? China, USA, or maybe Japan? They've already shown once before with the Earth simulator that they can also do this kind of thing. So next one, what's the European highest performance computing system? Is the EU Commission able to get into the top 3, and do we really need it? Then there's also the European Processor Initiative. So, for example, do we care about all the security issues that we have with the current generation of processors? Why would Europe then build its own processor? And would it be related to what we do? And the most important thing that we care about is, what are we going to do with the power that is dissipated from the system? For one, we're heating our own building, obviously. So that uses about 0.5% of the dissipated energy from the system that we use. So we have about 99.5% that we still have no use for. And there's the idea that to use an adsorption cooling machine. So the question is, how do we make beer from this with the hot water from the SuperMUC? So this is a very Bavarian answer to the question of what to do with the heat. So this is a very interesting project for us. We already thought about the labels, so we're quite far in that question. So this is the end for me. The slides are already uploaded. If you're interested, just look at them. If you have questions, just ask.
Thanks a lot for this fascinating talk, Dieter Kranzmüller. If you have questions, please use the microphones 1, 2, 3, 4, 5, and the internet. Damn. I thought I could ask my question first.
Thanks for the talk. Why did you decide completely against extra GPU system?
That's a good question. We didn't decide against it. We specified what needs to be calculated on the system. There's a number of codes that already run, and that's what the vendors got, and they saw what you can run on it. Of the 5 vendors, there were 4 that used accelerators, but the best performance we got without accelerators, and that's the best that came out of the competition. And I'm just as surprised as you are why this is like that.
Thanks for the interesting talk. My question is, do really only people from science and education run stuff on it, or is there also military?
Well, it's science, it's research and teaching. So it needs to be from research or teaching. I need to return the question. Is there military... in military research, is there anything that's scientifically relevant?
I have 2 questions. So, just one. Why did the guy with the bugs have to wait until the MOOC is completed, and why didn't he just use a different one?
The SuperMUC was the first computer that you could compute with all the properties. You also need the interplay of computational power, memory, and connectivity. And he knew that that was coming, and it would have that capacity. You can possibly compute that on larger systems, but the efficiency is a question. It was the best system for him to do it with. Thank you.
The internet has a question. How much do the users of the systems have to know about the architecture and adjust their programs in order to maximize the performance they're going to get from the system? And are there differences in the performance they get?
Yeah, to the second question, the best users are the physicists. It wasn't serious, but there are no metrics. It depends. There are enough programmers with more talent and with more brain capacity, you can do better. There's no metric who's doing better or not. To the first question, you need to know a lot. It's not only evaluated how that meets with the scientific requirements. How scientific is it? It's a question. It also has to fit the hardware architecture. So if somebody submits the code, they need to prove that it also scales, because otherwise it's a waste of money. Because all the factors have to match so that the system works accordingly. And yes, it's a lot of effort. We tried to cover it with a relatively large crew that gets together with the team and puts together the code with them.
Thanks for the talk again. You were saying that the system is cooled with water. What about the transformers? They also dissipate power.
That's right. The SuperMUC. We still have fans. You see that on one of the pictures of the SuperMUC, where the in-row cooler fans that the network components, the hard disks, are still cooled with fans. Here in the aisle in the middle, there are the fans. And this is still a disadvantage. We told the vendors that for the next system we also need to do it. We also have a small cluster which is CoolMUC3, which dissipates 97% of the power by water, and the power supplies are in a cage with holes for the water to go through. So we already cool all the components by water. It's a very good question. Thank you.
You were pretty open about what's being calculated on the computer, but you don't have an idea about what's being calculated on the other 10 in the top 10 list.
So when we look at the first 4 systems, it's Department of Energy, or it's working with the Chinese military, it's with military academies, and we don't know what, we have an idea what they do, but we don't really know. With the Swiss system, according what you just said, it's climate computations in the Swiss system, because you have a special code in Lugano. So it's very different for the different systems, for the different target architectures. The nice thing about our system is the breadth, that we can run a whole spectrum of applications. No other system has that.
Back to number 2. So in relation to the question before about what's being calculated in the other 10 systems, at the beginning of the talk, you were saying about the bidding system for the vendors. What are the proposals being done for, and what information is in there? What are you going to get from that?
So let's take an example. We have in the moment we signed the contract, we already prepared the next system. We already we already think conceptually about the 2024 system. In order to do that, we need to estimate what is available in 2024. So we have a non-disclosure with the Intel and IBM to have an insight into the roadmaps beyond what is publicly known. It gives it. We need to find out what processors are coming to make a concept for the next design. It's an interesting problem, but there are people who can't talk with us because it's necessary that we are very involved, very at depth, and to what we need to have as a concept, and we need to know the roadmap. We need to look into the future. So those are. Oh, so those are informations about the companies and not the. They're all handwritten codes. It's very open. It's a nice community, and if you go very deep in the code, and if we optimize that, we get involved.
Another question on the internet. How large is the proportion, or how much of what you're doing is political? How much is scientific?
That's a very good question. So officially, I'm doing only 25% of my time in the computational center, and the rest of the time I'm a teacher for distributed systems, a university teacher. So 25% of my working time is 4 days a week. So you get an impression. And I wouldn't estimate it. I won't complain. I have a dream job. I have a understanding family that allows me to be here, for example, while the family is at home. I'm here because out of scientific interest, because of the privacy and ethics that is also has related with the job. And of course, I have to be a little science manager. That's also in the whole paragraphs. It's nothing more sleep-inducing than paragraphs. I don't know if other people are like that.
Hi. I'm interested in the operating costs that are part of the budget. How long is the computer system gonna run for, and what's gonna happen to it afterwards?
So that's very simple. It usually doesn't pay off operating a computer like longer than 6 years. That was SuperMUC in 2012. We installed it in 2012, and the day after tomorrow, it's getting switched off. And at that time, the SuperMUC NG takes over the load. So that's the next processor generation. With the code porting, there's a difficulty. We have a system here, and it's too expensive to operate it longer. And in all those contracts, we have return options, so the companies can take it back. And if we compare that to the system before the SuperMUC, it was trashed in place, and the valuable materials were recycled. That's cheaper than just to continue operating it.
Someone said they have a power PC at home. That might be an ideal opportunity for you. Hi. How often does someone have to walk up to a rack and do some maintenance on it?
Basically, the double cube is a dark center. There is no offices there, nobody in there. At the SuperMUC NG, that's like that a lot of things has to be done. In the installation phase, in the normal operation, it goes down, effort goes down. We need to think about the number of components. The mean time between failure was at the SuperMUC was less than 1 hour. We had one critical failure within 1 hour. We can do most of the thing from the desk. So every once a day, somebody needs to walk over and do some maintenance in place.
How loud is it in there? Just out of interest, if you have a water cooling.
Good question. This is actually the quietest system because there are no fans. We are at a point. where in the aisles we have interviews. And the normal camera cancels the background noise. You don't get that in any other center. Next starter comes.
Sure. Thanks for the talk. You showed that there was a very, very long-running competition. Was using 50% of the first phase. Is it actually worth it to up the performance by 10% if you really don't use it that much?
So really used effectively or totally is we all use it correctly, even if it only reaches 10% of the maximum power, because you can still do things that you couldn't have done before. In science now, the systems are so big, the software, the data that you're using, you're making them so large that they can just be calculated on the system and on the volcanoes. Certain effects, and the Heiner Eagle talk in the Science Symposium, he shows that in his transparencies, he shows he doesn't see some effects. There are some effects he doesn't see because he can't calculate those resolutions. That means that the theoretical maximal peak power is a fictional number that is useless in principle. But the 44% utilization is relatively high compared to what else runs on it. It's not about filling the system consciously to maximum capacity. Somebody only needs 300 cores from the 311. We don't fill it up. So the next guy who gets the next guy gets a system that can fill it up. So we take into account the holes, and we don't use it up like Amazon because they're revenue based. Here it's science, and here it's to make science possible.
And we close the talk with this question, and a lot of applause for Dieter Kanzelmüller. That's also our finishing line. This was Kaste